started the recording. Okay. I hope you can see my screen. Do you have any questions from week 7? Okay. Do you have any questions from week 7 material? Any questions on Euler's equation and Bernoulli's principle? If not, let's just start with a short revision on what are the equations that we are dealing with, and then let's solve problems. Okay, so we will start by writing the Euler's equation. What is Euler's equation describing actually? So we have seen different forms of conservation: mass conservation, momentum conservation, and energy conservation. Right? So mass conservation gives us the continuity equation, and momentum conservation gives us this equation that I'm writing. So rho, total derivative d by dt of the velocity, is equal to rho g minus gradient of p. Now there are some assumptions that go into this equation. Can any one of you tell me what are the assumptions over here? Yeah, we have assumed it is inviscid. Okay, and yeah, so the only body forces that are acting is the gravity force. Okay. Okay, anything else? Have we assumed incompressibility? Yeah, have we also assumed incompressible flow? Okay. What happens if I assume incompressible flow then? No, so we have okay, so here the derivative, see, if we have the derivative as like this, total derivative of rho v, this is the momentum, right? So when we are conserving the momentum, then this rho was also inside our total derivative, but that is not the case in this equation. We have in fact assumed incompressible flow. Just give me a minute. Okay, so you can go back and look at the derivation of the momentum equation. What we start with is we give a, let's say we take a fluid element, and at time t its velocity is v. Then after some time the velocity is v t plus dt. Okay, but at this time the density is rho, and after some time it can be rho plus d rho. Okay, so using this transformation we derive the momentum conservation. If rho is not changing with time or with space, that means we have assumed the incompressible flow condition as well. Okay, now we also know, okay, so let me remove this. We we also know what is the total derivative. So total derivative d by dt is nothing but dou by dou t plus v dot grad operating on whatever is the function, right? So if we have a function or a vector, so in this case we have the velocity vector. So let me write the velocity vector here. Okay, and now if we further write the condition of incompressibility, that gives us del dot v is equal to 0. And what is dou v by dou t? What is dou v by dou t? That's the local acceleration of the particle, okay, fluid element that you have considered. So now you can write this equation in the x, y and z momentum, z directions. So let me write only in the x direction for you, and the rest follows automatically. Okay, so in the x direction we can write rho, so d by dt of velocity. So we are taking x direction, so v is actually having three components, u, v, w, right? So we are only looking at the change in u. So we have rho multiplied to dou u by dou t plus what is v dot del? So v dot del of v of and we are going to take only the x component. X component is v dot grad operating on only u. Okay, but here we have to take all the components of v. So first we'll write u dou by dou x of u, okay, plus v dou by dou y of u, then w dou by dou z acting on u. So I hope this is clear how we expanded the v dot grad term, and since we are taking only the x component, we are only operating this v dot grad term only on u. So in all the terms you will see there is u over here, and this is equal to rho into, if there is any x component of g, then minus dou p by dou x, right? So the gradient of p again has x, y, z components, so we are only taking the x component. So similarly you can actually write the y component, y direction equation, and what will change now? In this entire equation, what will change? Yeah, can anyone tell me? In place of u there will be v, okay. So over here, here and here, no, not over there, okay. So in the y direction we will have this as v, and u dou by dou x acting on v, v dou by dou y acting on v, and similarly the z component. And on this side, on the right hand side again, we have the y components, okay. So you have rho g y and dou p by dou y, okay. Similarly you can write the z direction equation, which I will not write. Now the other equation that you must have come across in this week's lecture is Euler's equations written in the streamline coordinates. So let's write in the streamline. What do you understand by streamline coordinates? Yes, anyone? What do you understand by streamline coordinates? Okay, what are streamlines? Anyone? So we solved a lot of questions on streamlines in the last class, right? Stream functions, streamlines. What are streamlines? Um, yeah, what you're telling me is that streamlines don't intersect with each other, because at the same point you cannot have two directions for the same fluid element. So yeah, that is, streamlines don't intersect. That is a property. But what is a streamline? Okay. Yeah. Hmm. Yeah. Exactly. So if I take any streamline, the tangent to this streamline at any point actually gives me the velocity of a fluid particle at that particular point. Okay. So that is how we define streamline. And now what we can do is we can define some coordinates. So what I'll do, I'll take one coordinate which goes along the streamline and one which is perpendicular to the streamline. Similarly, over here I can have, this is the along the streamline coordinate and perpendicular to the streamline coordinate. So what you can see is this streamline coordinate, like this S, it is changing its direction with respect to your rectangular coordinates x and y. So first over here the streamline is this S cap coordinate is oriented like this. Okay, then later on it becomes oriented like this, then it is changed further. So the streamline coordinate is not in the same direction fixed when you look from the xy coordinate, but that's fine. What we are saying is that I'm basically moving along the streamline, I'm seeing what is happening in the flow. So now I have changed my frame of reference. Okay, so now we'll write the equations. Okay, so 1 by rho, this is something you would have seen already in the lectures, I'm not going to derive this. So first I'm writing in the n cap direction. So 1 by rho dou p by dou n plus g dou z by dou n is equal to v square by r. Okay, so this is the Euler's equation, which is normal to the streamline and also for a steady flow. Steady flow, what is a steady flow? Yes? Yeah. At fixed time or fixed with time. Is there a question? Okay, properties do not change with respect to time. I hope everyone has been able to join now. Yeah, so that is steady flow. So any time derivative becomes 0, right? So here in this equation you see there is no time derivative. Okay, so let us first start by writing the acceleration. So let me write the acceleration along the streamline coordinate. This is given by the change in the pressure, so dou p by dou s, and if you derive this, there is also since I am writing the acceleration, so I have taken the density on right hand side, so there is a 1 by rho over here. Okay, acceleration is, remember, only dou u by dou t, this the du by dt term, so I have basically taken rho on this side. Okay, so I have a 1 by rho term here, and of course dou p by dou s and minus, and then we also have a minus g into dou z by dou s. So why do we have this dou z by dou s? So you can imagine that if the streamline is changing with z, so if let's say the streamline was oriented like this at this point, and at a later point it is oriented in the opposite direction. Okay, so the gravity force is always along the z cap direction, right? So with respect to s, the gravity vector should be taken always in the z cap direction. So that's why we get this term dou z by dou s over here. Okay, and how do we write this as? As is nothing but dv by dt, which you can write in the expanded form. So this is dou v by the vector. Okay, so dou v by dou t plus v dot grad, right? So v dou by, okay, so just a second. So we are writing only in the s direction. So we have dv by dt is equal to dou v by dou t plus v dou v by dou s, and we can simply write v. Why can we simply write v? Because along the tangent the entire velocity will be considered, right? Okay, somebody is trying to join. Yeah, so the entire velocity vector, the value will be along the tangent, this s cap direction. So we have dv by dt is written as dou v by dou t plus v dou v by dou s. Okay. Now what about an? So an can be written as minus 1 by rho dou p by dou n, right? Similarly, similar to the as coordinate, and then you have minus g dou z by dou n. Any doubts still here? No. Okay. So now we had, let's again consider the streamline, and at this point I'll draw a tangent. Okay. So if I draw this tangent, now the velocity is completely along this direction, right? So this is the velocity, and this is also the s cap and n cap directions again we can draw here. So s cap is this and n cap is this. Okay. So I can say that the velocity in the n cap direction is 0. So how do I find the acceleration now? Is the acceleration 0 or non-zero? Acceleration in the n cap direction, will it be 0 or non-zero? Non-zero. Why? Yeah, that is on this side. So we have this term. This is the force balance term, right? So the pressure force and the gravity force that will induce. But what about these coordinates? Like what I have done over here is I have taken dv by dt. This is the total acceleration, isn't it? d by dt of the entire velocity, and that gives me dou v by dou t plus v dou v by dou s. Is there any other term that I am missing? So what kind of acceleration is this pressure and gravity force giving in the normal direction? Due to the curvature, exactly. So if you see, you can draw an instantaneous circle over here, okay? And let's say its radius is r. So you must have studied in your elementary courses that if there is a particle which is moving in a circle, so it will experience a centrifugal force, right? So if it is just moving along this circle and this is the radius, it is moving with some velocity, let's say u naught, then what is the centripetal force or centrifugal force that it experiences? So here it is u naught square by r, right? So the same thing is going to apply in this case. So there is an instantaneous circle. Instantaneous because in the next instant, as the fluid element moves forward, it is possible that this circle has become a much larger or a much smaller circle. So the circle radius itself is changing in time, which is okay. But at an instant, I can write that an is proportional to this, whatever is the velocity, that same velocity as what we have written here. So v square by r. And this acceleration will be negative because v square by r is the force that is pulling the fluid element into the circle, right? So in the n cap direction, it is actually negative. Okay, so if you put this back into this equation, you will get what I had written here. Okay, and similarly we have also the equation in the s cap direction. Are there any questions for this? No? Yeah. Minus g dou z by dou n. Okay. So there is a derivation actually for this. Let me see if I can do the derivation here. I'm sure this must have been derived in your lectures as well. Okay, so let's say these are my streamlines, and I consider a fluid element over here. Okay, and this is your S cap and N cap. So let me draw this enlarged. So this fluid element is going to experience some force, inwards force, that is the pressure, right? So here I can say, let's say at this center the pressure was P, and remember this direction is S cap and this direction is N cap. So if I go forward in S cap, I'll say the pressure increases, and let's say it is P plus dou P by dou S, okay, into, so this length was ds, so I have gone forward only by half of ds. Okay, so this is P plus dou P by dou S into ds by 2. That is the increase in pressure as I move forward. And what is the area over which this force is acting? So this length is along the n cap, right? So I can say the length is dn, and you can imagine that into the plane is, either we ignore into the plane or we can just take it as some length. Okay, so I am going to write dx. Yeah, so this is y into the plane x, y, sorry, out of the plane. Out of the plane is x, and this direction is z. And we know that the gravity is acting in this direction. So similarly, I can write the pressure on this surface, so that is P minus dou P by dou S into ds by 2, and then similarly we will multiply dn into dx. At the top surface, as we move in positive n, again we can say the pressure increased by dou P by dou n, because you moved forward in dn amount, dn by 2 amount. And then you multiply with this surface area, which is in the s direction, so you will say into ds into dx. Okay, and yeah, and similarly here you will write P minus dou P by dou n into dn by 2 multiplied to ds into dx. So is this clear how I wrote these pressures? Yeah, okay. Something's happened to my so ds into dx. Okay, so if this is clear, if you apply the Newton's second law, so how will you write the force balance? First there is a pressure balance. So what is the pressure balance? Let's do it in the s direction only. So in the s direction, what is the pressure difference? The pressure difference comes from, I have to take the difference in on this surface and on this surface, right? So basically I have to subtract this term and this term. So the p and this p, they just cancel out, and this dou p by dou s ds by 2 minus into minus, so that becomes plus, and dou p by dou s into ds by 2. So half and half, we have just added it. So what we get at the end is dou p by dou s into ds by 2, okay, multiplied to dn and dx. Now this is acting in what direction? Plus or minus s cap? Minus. So I'll put a minus sign here and s cap. Okay, and what about the gravity force? So let's draw the gravity vector here, right? So the gravity force is now supposed to be split into this s cap and n cap. So if you consider that s cap, let's say it is in some, at some angle, okay, and similarly you have n cap, and let me say this angle is, let's call it beta, okay. So how will you write the gravity force now in the s cap direction? See, this gravity force which was acting in this direction, you will have to split it here and here, right? So if this is beta, this is also beta, this is g cos beta, and this is g sin beta, and g sin beta is also acting in the minus s cap direction. So going back to the equation, now I can say is a minus g, okay, this was a force, by the way, dou p by dou s, this is a force, so I have to also take rho into g, so rho into g sin beta, and this is acting on a volume. This is the gravity force which is acting on a volume, which is given by the elemental lengths ds, dn, dx, okay, in the s cap direction. And these terms together balance, or they produce the acceleration in the as direction, okay, for the volume ds, dn, dx, okay. Now what we will do is, obviously we'll divide by ds, dn, dx in all terms, and this sin beta term will give us the dou z by dou s. So let's do this. So sin beta, how do you write sin beta? Now in this case you had, this was your s cap and this was your z cap. Now as you change the angle, as s cap changes, the beta is also going to change. So sin beta is nothing but, so let me again try and draw this. So this was your g, this is the s cap, and this is your n cap, and this is nothing but z cap, right? So this was beta. So any change ds and any change dz and any change dn are going to define this beta angle, right? So I can write sin beta is nothing but dou z by dou s. Similarly, you can also define cos beta, okay? Is this part clear? Yeah. So now if you put sin beta into this, and then you divide by ds, dn, dx, you will recover this form that we just now wrote, dou z by dou s, okay? And similarly, when you write the acceleration in the normal direction, you will get the g cos beta term, right? And this g cos beta, so cos beta can now be written as dz by dn. Yeah, so that is the term we have, dz, dou z by dou n. Okay, I hope that clears how we got this equation. So I am not writing the entire derivation, but these are the main steps. Okay. Any other questions? Okay, so what you can observe from these equations is that in the normal direction, you have the terms dou p by dou n and dou z by dou n. So the pressure increases in the direction which is outward from the center of curvature, and there is no pressure variation which is normal to a streamline where there is no curvature, right? So for example, if I consider very straight streamlines like in a uniform flow, right? So in a uniform flow, there is basically no curvature. So what will happen in this equation, because this term vanishes, there will be no pressure variation at all. So if I am going from this point to this point, there is no pressure difference. P over here and here is going to be same. And that should be very obvious, because if there was any pressure variation from P1 to P2, if let's say P2 was higher, then the flow should go from P2 to P1, right? We know that flow will move from high pressure to low pressure area. So if there is a flow where the streamlines are just straight lines, then it is obvious that the pressure is not varying in the normal direction to these streamlines. Okay. So this you can see from the equation as well. Okay. So if there are no questions, we can start solving some questions today. Yes. Yeah. Yeah, tell me. Let me add it also. I'm solving term 2. Yeah. Yes. Okay, I think you are giving me an equation from the lecture, is it? Can you please tell me again? Yeah, V dot that acting on V, yeah, is equal to half of gradient of V dot V, okay, minus V cross curl of velocity, right? Yeah. So this is the equation from the lectures, okay. So what is the doubt? Yes, it is an identity. So in fact, what you can do is you can check out the identity A dot grad of B vector, okay, and you can verify that this is true. The left hand side and right hand side are true. So how to do that? So we looked at the Einstein notation in, I think, the last to last class. So if I write B as, let me write this, B vector is nothing but B1 I cap plus B2 j cap plus B3 k cap. Okay, so what is Einstein notation? It will say, let me just call this Bi. So it is understood that B1 is in the first direction, B2 is in the second, and B3 is in the third, and it is understood that I goes from 1 to 3. Okay, so there is a shorthand notation of vector. Similarly, I can write A. I'll write it as AI. Now the grad vector, so this is an operator. This operator goes like dou by dou x in the I cap direction, plus in the j cap direction you have dou by dou y, and in the z cap direction, k cap direction you have dou by dou z, right? So we will write this as dou by dou xi. So it is understood that at I equal to 1, that means in the first direction it is dou by dou x and so on. So again, this is a shorthand notation where if you see, I am not writing I cap, j cap, all these things are not written. It is understood, implicit. Now let us see A dot grad B. So what does A dot grad of B give? It is AI. So A dot grad, remember, it is like A1 into dou by dou x. Okay, so it will have terms like A1 into dou by dou x1. So instead of xyz, what we can do is we can write this as x1, x2, x3. Okay, so there will be terms like A1 dou by dou x1 plus A2 dou by dou x2 plus A3 dou by dou x3, right? So here I'll write AI dou by dou xi, that's it. So when there are two indices repeating, it is understood that there is an addition. So in this case, it is understood that AI dou by dou xi actually represents this particular expression. Okay, and then the B vector you can write as Bj. So this entire operator can act on B1, B2, B3. Remember, because if you go back, this is how we wrote. See, U dou by dou x, V dou by dou y, W dou by dou z. All of these are acting on U. And then the same terms, U dou by dou x, V dou by dou y, W dou by dou z. All of these are acting on V. So the same thing is happening here. We have this operator, A1 dou by dou x1 plus and so on. And that can act on B1, it can also act on B2 and so on. So you have a vector over here. So when there are two indices repeated, there is a summation. When there is one index which is not repeated, this means that this expression is actually a vector. Okay. Now similarly, what you can do is you can take the right hand side. So what is the right hand side? They have said, according to this identity, the right hand side is actually half. If I take A dot B, so it is del so I think it's del A dot B so let us, for now simplicity, let's take the same vector, because I think there will be many terms and this boils down to a symmetry. So A dot grad on A, so half del A dot A, right, minus A cross curl of A. So this is the identity. So instead of B, what we have now is AJ over here. And on the right hand side, you can verify whether this is true or not. So let's start by the RHS and write it in the Einstein notation. So this is half dou by dou xi, okay, dou by dou xi acting on A dot A. A dot A, so that is a dot product, right? So I can write this as AJ, AJ. But since on the left hand side I am taking J to represent the vector, okay, excuse me, let me first write the inner bracket. So that's AI, AI, and the vector term comes from the J coordinate. So I am going to write dou by dou xj. Is the first term clear? How did we write this first term? Not clear. Okay. Do you know the Einstein notation? Yeah, okay. So A dot A, if we multiply, you agree it is AI. Okay, and then we are operating this grad term on A dot A. So grad term is represented by this dou by dou xi, right? So dou by dou xi, I have just taken a j coordinate. Why? Because see, on the left hand side, what is the independent variable? J. Here ai and dou by dou xi. So I and I, they have gone into the summation. The vector is represented by the j index. This will also go from 1 to 3. Here also j will go from 1 to 3. We are just being consistent on the left hand side and right hand side. Okay. And the third, the last term is this A cross curl of A. So first let me see what is curl of A. This again we saw last time. Curl of A is written as EIJK. So I'm just going to write it so that I have J as my independent index, JKI. Okay, dou by dou xk into AI. Okay, and then what is left is the J coordinate. So we are going to take now the cross product with A. So A cross this. Okay, so this is, let me take some other indices. So let us start with the innermost bracket again. This is epsilon dou by dou x A. So let's take LM n, and this is m, this is n. Okay, and this is the vector which is given by the L cap L going from 1 to 3, right? Now this A is written as AI, I going from 1 to 3, and you will have an epsilon. So epsilon j, here we had L, so j I L, this vector, and the AI vector. Okay, so this is how this term is written. It is a little, it takes some practice to be able to write these terms in the Einstein notation. But once you have done this, there are many properties. See, you can just simply rewrite this and take epsilon JIL and epsilon LMN, and then you can combine this AI dou by dou XM AM. Now you see there are two, these are called Kronecker deltas. So epsilon JIL and then epsilon LMN. So there are properties when there is one common index, like this L is common, right? So I don't exactly remember all the properties here, but if you apply those properties, you basically have to put this back here into the RHS, and if you apply those properties, then you can show that the left hand side and the right hand side are in fact equal. So you can see, like without even evaluating, you can see that there are some terms like A dou by dou x A, and that's exactly what you want on the left hand side, A dou by dou x A. So only some terms will survive from this expression. You will get certain terms which are of the form dou by dou x A into A, and of the form A dou by dou x A. These terms will cancel with this part, and these terms will survive, and they will be equal to the left hand side. Okay, so this is in fact an identity that you can prove. Yeah. Vector triple product, no, because this is an operator, right? No, that will not work. A cross B cross C will not work because this is an operator. So you have to take the derivative, and okay, in A cross B cross C, for example, there will be some terms like B dot C. So then you have to remember that it has to operate, whether it has to operate like a divergence or whether it has to operate like a gradient. So these terms you'll have to see. Like if you have B dot C and you have C dot B. So in the B dot C, it will be like del dot A, but in the C dot B, it will be like A dot del operating again on A. So these are the kind of terms you'll have to deal with, which is fine. If you convert it properly, it is possible. Yeah. I think I can direct you to try and do it. Why don't you try and do it on your own? There is a lengthy derivation. You have to basically start from the right hand side. Okay. Okay. This half term you are not getting. And instead of using this identity for V cross grad cross V, you have used A cross B cross C. Is that right? Yeah. Yeah, A and C are equal. Okay, let me write down one identity for you, which I can quickly write over here. And why don't you check if this is what you got? See, what you have done is, like you said, you have taken A cross B cross C, and A and C are equal, so this is V and V, but this is grad. This is what you have done, right? Yeah, but I would suggest using this. So A cross curl of B, and when you take curl, it is not the same, it's not exactly same as B cross C, but there should be an analogy possible immediately. So why don't you just check if this is what you did. So the identity is like this. So A cross curl cross B is okay, so you'll have A dot B term and grad operating on this minus A dot grad operating on B. Okay. Yeah, that's pretty much it. And if you take A cross B cross C, you see how that turns out to be. To avoid confusion, let me write A cross C cross B. Okay. So C should be, we should be able to replace with the grad. Okay. So let me see the identity here. Yeah. So this turns out to be A dot B and C vector minus A dot B. Oh, sorry. A dot C and C vector minus A dot C. Just a second. Yeah, no, it will be A dot C. Yeah, in Now the problem with this approach is, see, if you replace C with just grad, you should get A dot grad operating on B minus again A dot grad. Oh, I've written both the terms same. No, the reason is the over here it is, yeah, no, the reason is I got confused because I've written C in between, so that is the problem. Let me try and write this again. So A cross C cross B, so that will be A dot B on C minus A dot C on B. Now it is correct. Yeah, so now C we have to replace with grad. So C if you replace with grad, now see what happens is you are able to immediately write A dot B, but grad operating on what? So you have to understand how this gradient operator works, and if you have not written it correctly, then there will be some problem. So it has to be grad operating on this A dot B, and then here it is A dot grad operating on B. So ideally you should get the same expression, but I don't know if you have proceeded in this manner, because see, the point is this triple product gives a vector, okay, and this whatever we did here, A cross grad A cross curl of B, right? So this, if when you expand, it gives you a vector. Now the first term, the vector comes because of this operator, gradient operator operating on this term, and here the vector comes because first you took this A dot grad and then it is operating on the B vector, okay. So it is in fact the B vector which is more important here it is the gradient which is giving you the vector. So I don't know how you proceeded with this triple product, whether you wrote this correctly. So why don't you try using this identity once and then try and derive. Okay, we just have to put B vector, right? So you get B dot B minus B dot grad which is this term. Okay, so perhaps there's a mistake in this identity, or let me just check this and get back to you. There is usually a half. Okay, I will check this and get back to you. So your question is, this half is not getting cancelled. Okay. Good. Alright, yeah, I will look into this and get back to you. Any other questions until then? Anyone has any other questions, or anyone knows what's going wrong here? Galilean frame. Where did you come across this? Okay, I'm sorry, I'm not aware of this. I mean, I know what is a Galilean frame, but I don't know what that means. You can post a query on the portal of NPTEL. Yeah, actually, I'm not able to find this identity that you just dictated me, this identity anywhere. I just did a quick Google search here. I'll look into this identity, what is the correct form, and get back. But perhaps we are just making some mistake in this transformation. Okay. So let us start with some numerical questions until then. Yeah, what we have is a curved duct, what you can see over here. So this is the top view and this is a three-dimensional view. So in fact a cross section of this pipe, of this duct, is rectangular, but there is some curvature, there is a bend. Okay, so the flow rate of air in the standard conditions in a flat duct is to be determined by installing pressure taps across the vent. The duct is 0.3 meters deep, 0.1 meters wide. The inner radius is given, and I think, yeah, the thickness is also given, so you know the outer radius. If the measured pressure difference between the taps is 40 mm of water, so it is given in height of water, but we can convert it to kilopascals. So what we need to find is the approximate flow rate. Okay, so what is happening here is, see, this is something very practically useful. So if you have a, let's say, a pipe, what you can do is you can stick in pitot tubes or manometers, right? And let's say I measure the pressure at two different locations, P1 and P2. And let's say I know that the area of the pipe remains constant, I can assume smooth flow, frictionless flow, and so on. And I know that there is a change in the pressure. There's going to be, whether pressure is going to increase or decrease. Can you say if the pressure will increase or decrease? If we are assuming frictionless, well, it can increase or decrease. Usually it will decrease if you are just letting the fluid flow through. But if you are pumping in energy, let's say if I am pumping in energy at this point, then there can be a pressure increase. But if I am not pumping in any energy over here, then the pressure is going to decrease. Okay. Now the change in the pressure will tell me what is the flow rate. So this is something that is done practically. We measure pressure at two stations, and that helps me determine what is the flow rate through the pipe. So that's what we have to do in this question. Alright, so first let us see what is the pressure difference. So delta P. What we are doing is we are measuring pressure at two locations. That's what is given to us, 1 and 2. So P2 minus P1 is equal to, the pressure is given as 40 mm of water. How do we convert that to kilopascals? Yeah, how do we convert 40 mm of water into kilopascals? It's quite a straightforward formula. H by rho g, no, H into rho g, right? Rho g H is the pressure. Yeah. Okay, so rho of water, because the height is of water, right? And into g. So let's do this. We have 40 mm, that is 40 into 10 to the power minus 3. Density of water, let us take it as 1000, and gravity will take us 9.8. So can you tell me what is delta P? Please calculate and tell me what is delta P. 392 watt Pascal. So that is delta P. Now what do we need to find? We need to find the flow rate. Let me call flow rate as Q. What do you understand by flow rate, by the way? What is the formula of flow rate? Area into velocity, that's it. Yeah. In this case, the area remains constant, and we are assuming that there is some constant velocity. So velocity into area. Alright. Now, what is the governing equation? There is mass conservation, of course, but that is not going to give us the flow rate, because we need to find the velocity with which this fluid is moving. So we have to do momentum conservation, and we are going to assume inviscid flow, incompressible flow. So with all these assumptions, we boil down to Euler's equation, and the immediate question comes is, in what frame of reference should I use this Euler's equation? Okay, so here it is easier for me to define my coordinate axis along the bend. See, if it was a straight duct, then I can just define x and y axis, right? Or if it's a circular straight pipe like this, if it is something like this, then I can use r, theta, z coordinates. Here we cannot use either of these things. What we can use is the streamline coordinates, because the flow is going to move along this duct, along the bend, and the streamlines are also going to be along this bend. Okay, so we are going to use the Euler's equation. So let us first write the normal direction. Now in the normal direction we have dou p by dou r. So dou p by dou n. We first write n. Dou p by dou n plus, okay, there is a 1 by rho, plus g dou z by dou n is equal to v square by r. Okay. Now there is no funny curvature in the z direction. So for example, if this is my z direction and x and y, so you see the bend is only in the xy, it's not in the z direction. In the z direction would mean that there is a change along the z axis, but that's not the case. So I can say this term is just 0. Okay, and what is the n cap direction along the bend? So you can see in this diagram, along the bend is this radial coordinate. So I can, instead of n, I can write dou p by dou r. So I'm going to write 1 by rho dou p by dou r is equal to v square by r, right? And it can be any, like at any instant it can be some radius r. So we're just going to say v square by r. Okay, so you can see that at this point the radius would be r1, but at this point the radius will change to r2. I hope you can appreciate this. Are there any questions about how we are going to solve the n cap direction? or why we are using the streamline coordinates? Please stop me anytime if you have a question. Okay, now what are the assumptions that we are making? So let me write these assumptions here. So the assumptions that we are making, first of all, is that there is no friction. Okay, so it is a frictionless flow. What other assumptions do we have? Anyone? Okay, so if you see, there is a measurement which is made at the center at some location. So this is made at, let's say, the bottom line of this duct at the center location. Here it is made at the top. So we are actually assuming that there is a uniform flow at a measurement section. So at any section that I have taken, so this section is drawn for you, whether I measure at the top or the bottom, it does not matter. There is a uniform flow. This is an assumption. So uniform flow at certain cross section. And of course we have incompressible inviscid flow assumption. Now because we have this assumption that uniform flow at any cross section, that's why we can write this equation in this simple form, that dou p by dou r, now I'm going to write as dp by dr is equal to rho v square by r. If this was not the case, if we had not made this second assumption, then we could not remove this term dou z by dou n. We could not remove that. Okay. Any questions still here? No. Okay. So now we can simply solve this. So you see there is a dr over here and r over here. So we have to just put these terms together. So dp is equal to rho v square dr by r. And again, at a cross section, uniform flow means velocity is same at that cross section, throughout that cross section. So this velocity is not changing with the radius or with the z axis, but it can change from one location to another. So here, with respect to this r coordinate, there is no change in the velocity. Okay, and pressure change we know already. So I am just going to integrate this. Pressure change is the delta P, which we have already found over here, 392 Pascal. Okay, so this delta P is equal to rho v square, and dr by r integral is log r, and this goes from radius r1 to r2. So there are these radius r1 to r2. Okay. Further, you can just rearrange this and you can say, okay, what is the velocity in terms of the change in pressure? So that's delta P divided by rho log r2 minus log r1 is nothing but log r2 by r1. And there was a v square, so this is to the power half. So this is the relation. And we already know delta P, so you can plug in the values and find the answer. So let me just add a page here. Yes, so we know delta P is rho g h h2o, and this we have found is 392 Pascal. And again, this density we will take as water, because I think it's given in the question that you can assume the flow is given for air. Sorry. So here we have to assume air in this is rho air, and you can take density of air as 1.23 kg per meter cube. Okay, and R2 and R1 are also given to us. So R1 is the inner radius, which is 0.25 meter, and the thickness is 0.1 meter. So R2 is 0.35 meter. So let me write this here. R1 is 0.25 meter and R2 is 0.35 meter. So can you plug in and tell me what is the velocity? Please calculate this and tell me the answer. Yeah, so we can take it as 30.8. 30.78 is approximately 30.8 meter per second. Okay, so we had to find the volume flow rate, which is Q, that is velocity into area, and the area can be found. So area is this area, right, which is a rectangular surface. So that is 0.1 meter wide and 0.3 meter in height. So the area is 0.1 into 0.3 meter square, and that multiplied to this velocity, which is 30.8. So what do you get as the answer? This will be in the units meter cube per second. .924. Yeah. Okay, I hope everybody got this answer. Any questions about how we wrote the equations? So let's move on to the next question. Okay, so now what we have is a pitot tube, and it is inserted in an airflow to measure the flow speed. So this is some duct here, and there's a flow in this duct. Air is flowing here, and what we do is we just plug in a pitot tube, and we want to measure the pressure here. So the tube is inserted such that it points upstream into the flow, and the pressure sensed by the tube is the stagnation pressure, and the static pressure is measured at the same location in the flow using a wall pressure tab. So before we proceed to solve this question, let us first understand what is static and what is stagnation pressure. Static versus stagnation pressure. Can anyone tell me the difference? Yeah? Somebody says something in the chat. Okay. I'll probably get back to this question a little later. Can anyone tell me what is the difference between static, stagnation, pressure? Okay, when we were solving this question, we said the pressure between two locations is given to us, and that's 40 mm of water. What did you understand by that pressure? What is it? The pressure is of what? Yes, anybody? What is static pressure? Or what is pressure? Yeah, go. The force per unit area. Okay, so the way we derived this momentum equation, we said, okay, let me consider this fluid blob, and it is experiencing some force from its surroundings because other fluid blobs are going to exert pressure because of some random motion between molecules and so on. And there is going to be this pressure, right? So this is the pressure that is felt by a fluid particle as it moves, and this is called the static pressure. Okay, even though the fluid particle is actually moving, but we call it static because we are not taking into effect the kinetic energy. So as a whole, what happens is, okay, you can consider two different cases. Let's say we have a tank, okay, and there is fluid fill in this tank, and this, at this point I measure a pressure. So that is going to be because of the atmosphere plus the height over here of this fluid. So we can say that the pressure is nothing but P naught plus rho GH. And this is something we have been solving for quite some time, right? So this is the pressure that we measure over here. And this is called the static pressure. But now imagine that you have a jet, okay, a jet of water. And you have this plate over here. So there is going to be a jet of water, and just for consistency, let me do one thing. Let's make it in the vertical direction. So let's take a plate over here, and let's assume that you have some pipe from which the water is falling. Okay, so there's this jet which hits the plate at the bottom, and let's say that the total pressure that is there in this amount of fluid, the same amount of static pressure is filled in this fluid. So will this plate experience the same pressure? Yeah, so there will be much more pressure felt because of the motion, because of the total motion of this jet, and that kinetic energy is going to be converted into the pressure energy at this flat plate. Okay, so that is going to give additional pressure, and that is what we call as the stagnation pressure. So in fact, what we can do is we can write this in two terms. So we can say that there is pressure P and there is a pressure due to kinetic energy. Kinetic energy is half rho v square. Now if this kinetic energy somehow I am able to convert to pressure energy, then that is going to add to the static pressure. Okay, so this part is called the static pressure, this part is called the dynamic pressure. Okay, and this together makes up for what is called the total or the stagnation pressure. Okay, now you see the question. So in the question you have two openings over here, right? One is here and one is here. Now what is happening to this? It is experiencing the flow. So the flow is basically hitting over here. So it is actually analogous to this situation where there was a jet hitting the flat plate. So what this is going to measure is whatever is the pressure in the airflow. So the fluid blob is experiencing some static pressure. It is going to measure that also. So it is going to measure this P, and because of the motion, because of this uniform flow, there is some impingement onto this point, and that is the dynamic pressure. So what is measured over here at this location is going to be the stagnation pressure, but what is measured over here is only because of the whatever is the fluid blob that is experiencing. So you can in fact imagine that you zoom into this location. Actually the fluid is moving like this, but there are the molecules are in fact moving very randomly. So whatever is experienced here is only the pressure experienced because of the random motion of molecules. Okay, so this is the static pressure that we are talking about. So is this clear why we measure static here and why we measure stagnation over here? Okay, so now the question says, so we are measuring static and stagnation pressure at these locations, and the static pressure is measured at the same location in the flow using a wall pressure tap. If the pressure difference is 30 mm of mercury, you have to determine the flow speed. So now given this formula, in fact it becomes very clear what we are given is, we are given static pressure, we are given stagnation pressure, and we have to find the velocity. So velocity is nothing but, I can just rearrange this, v square is p naught minus p into 2 divided by rho. So velocity is under root of that. Okay. Now what is the pressure given to us? 30 mm of mercury. 30 mm Hg. This is the pressure of this is the pressure difference. So that is P naught minus P. So difference between the two locations that we have measured. So stagnation minus static is delta P is 30 mm Hg. So we can convert this to pascals. How do we convert that? Again, rho Hg into gravity into this height. So what is density of mercury? Do you remember? Okay, that is in what units? Okay, so 13.6 kg per meter cube. This is the correct units. Okay, and 9.8 meter per second square, and 30 mm is converted to meters, so 30 by 1000. Okay, so that's rho gh. Okay, so what is this delta P? (13.6) is the specific gravity. So 13.6 into 1000. Yeah. Yeah. So you were what you mentioned was, I think, 13,600, right? Yeah. So this boils down to that. Now you can plug this delta P back into the velocity, and over here, remember what is flowing in this duct, that is the density we have to use in the formula, right? So here the density is going to be of air, 2 into this delta P, which you tell me now, and density of air we are taking as 1.23 and an under root. Yeah, so what's delta P? Can you repeat? 40 kilopascal. Okay. So you can plug in this 40 into 10 to the power 3, or in fact you can try and plug in a more accurate value and see what is the velocity. No, that's not right. That is not right. So please check your delta P calculation as well. Four kilopascal. Okay. So now what is your answer? Velocity? Yeah, 80.6 meters per second. That's correct. This is approximately like 4 kilopascal. Okay. Now, one thing you can check, we were talking about flow of air, right? So, for flow of air, we know the speed of sound. Speed of sound, the sound speed in air. Do you know the approximate value? 343 meters per second, right? And given this velocity, the Mach number will be basically this velocity by the speed of sound, right? So you can divide 80.6 by 343 and tell me what is the Mach number. Something like 0.2. Yeah, 0.23. So this Mach number is well within 1, and hence the assumption of incompressibility is valid. Okay. Why is this condition of incompressibility important? In any of our equations, have we used this condition of incompressibility? We have considered that the density is constant. You just assume that whatever change, see, P naught minus P is what you have measured experimentally, right? But whatever is change in the pressure, it could be because of change in velocity and also because of change in the density. But the change in density is neglected. This is the reason why we are able to take density on this side, assume density as a constant, and solve for velocity. Okay, if the assumption of incompressibility was not valid, we could not write this equation. Okay. Any questions till here? Okay, so what we can, let me just add a page. What we can immediately see is we have actually used a form of the Euler's equation right now. A form of the Euler's equation which is known as the Bernoulli's equation, which again you must have seen the discussion in the lectures for this week. So what the Bernoulli's equation states is that the pressure head P by rho, velocity head V square by 2, and the potential energy, Gz, this quantity remains conserved if we assume that there is a steady flow, incompressible inviscid flow, and we are measuring these quantities along a streamline. Okay, so this is very important, that the flow is along a streamline, and of course there is frictionless conditions. Okay, so inviscid, incompressible, steady. But one very important thing is that the flow should be along a streamline. So I can say that, let me call this as some quantity q. This quantity q, and this is a streamline. So the quantity q is going to remain conserved along this streamline. So this is Bernoulli's equation. And often what you will see is that we are applying Bernoulli's equation left and right at every point in the flow. But that is not valid always. It is valid under very special conditions. So if you go back to the derivation of Bernoulli's equation, you'll see that this is constant only along the streamline. So you can go back and see the derivation, but for now let me just write this. What you can get as your equation is dp by rho plus v dv plus g dz. So these are the equations we wrote along the streamline. Yeah, so we had this dou p by dou s, dou z by dou s. So we are, if you solve this further, you had this dou v by dou t plus v dou v by dou s. Now dou v by dou t vanishes if it is a steady flow. And along this streamline, if I find the change only along the streamline, so you have these terms v dv and dp by rho and g dz, right? So I'm just combining, let me write it from here. So from here, in fact, you can see this is straightforward. You have dou v by dou t plus v dou v by dou s. There's a minus sign here, so minus 1 by rho dou p by dou s minus g dou z by dou s. And if we have steady flow, then this term becomes 0. And if I say that I'm doing this, I'm going to do the integration only along a particular streamline, so I can take all the terms together. I can say v dou v plus dou p by rho plus g dou z is equal to dou s over here. So you see what I have done is, I have collected the terms that are varying on one side, and on the other side I have dou s. What is dou s? Change along the streamline. And if I integrate this like this, then what do I get? I get v square by 2 plus p by rho plus g z plus some constant is equal to this integral along the streamline. And this will be constant. This will be constant only along that streamline. Okay, so you see that your Bernoulli's equation is valid only along a streamline, and still we are able to sometimes apply it all throughout the flow. When can we do that? Under what condition can we do that? No, that we have already applied: steady, inviscid, incompressible. And with these conditions, we have derived that this quantity, this p by rho plus v square by 2 plus gz, this entire expression, this is constant but only along a streamline, isn't it? Yeah, so when can I apply this for the entire flow? That is my question. the flow is irrotational, okay, but still in an irrotational flow the streamlines can be converging or diverging, right? See, what I'm saying is that if I have a streamline, then at some point, okay, we call this point 1 and another point 2. So point 1 and point 2, I can say that this quantity is conserved. But if I had another streamline here, let's say point 3, can I say that this expression v square by 2 plus p by rho plus gz is same between point 1 and point 3? Can I say this? No. So when can we say this? Yes, but when can I say that it is constant for point 1 and 3 also? What flow condition can I say this in? Yes. Any guesses? See, you have already exhausted. Yeah? Go ahead. Streamline condition. What is streamline condition? On the same plane. But this is also in the same plane, right? See, these are two different streamlines. So if I call this as some quantity q, I can say that q1 is equal to q2. But when can I say q? Right now q1 is not equal to q3. But when can I say q1 is equal to q3? Yeah? So one of you said irrotational flow. Why did you say irrotational flow? What happens if we have irrotational flow? Irrotational flow is 0. No. Curl of velocity is 0. That is irrotational. Huh. See, yeah, so when we have curl of v is 0, then you can in fact show that in this equation, you can in fact show that there is no dou s, like there is no change from one streamline to another stream. Okay, so there are streamlines, there are potential lines, but in an irrotational flow, I can also compare between point 1 and point 3. Okay, so if we have time left at the end, we'll probably try and derive this. Okay, so for irrotational flows only, you can say that q1 is equal to q3. Okay. Otherwise, we have to be careful and we have to apply Bernoulli's equation along 2 points which are on the same streamline. Alright. Okay, So let us solve this question. We have air flowing through a nozzle. So what is a nozzle? Nozzle is basically a device where you keep decreasing the area, and by virtue of this decrease in area, the velocity increases. Okay, if the velocity increases, what happens to the pressure? Okay, yeah. Yes, yes. Okay, it decreases. So let us solve this question. You are given the area at the nozzle inlet, which is inlet is A1, 0.1 meter square. Nozzle exit area, which is much lesser, is 0.02 meter square. We have to determine the gauge pressure required at the nozzle inlet to produce an outlet speed of 50 meters per second. So there is some pressure that we are applying across this nozzle device, which is propelling the flow forward, right? And we have to find this gauge pressure that is required, so that at the end of the nozzle, the flow that is coming out has a certain velocity, 50 meters per second. So we can apply Bernoulli's equation at point 1 and point 2, because the flow is going to move like this, converging, but along a particular any streamline, this quantity that we just discussed, v square by 2 plus p by rho plus gz, this is going to remain conserved, right? So I'm going to take the center streamline and apply Bernoulli's equation at this location 1 and 2. So let us write this down. P1 by rho plus v1 square by 2 plus gz1 is equal to P2 by rho plus v2 square by 2 plus gz2. Now immediately we can see they are at the same same height, so this and this get cancelled. Okay, and of course we have made the assumptions of incompressible and steady flow and uniform flow. Okay, so how do we find this pressure difference? So P1 minus P2 by rho is equal to v2 square minus v1 square by 2, right? And we know that P2 is, it is given that P2 is P atmosphere, and the question is what is the pressure required at the nozzle inlet. So nozzle inlet is here, right? So we have to find P1, and P2 is given to us as P atmosphere. What is V2? V2 is the required speed, 50. And what is V1? Yeah, V1. What about V1? Yes, we will have to find V1, and for that we use the continuity equation. Okay, so continuity states that, in fact, rho A1 V1 is equal to rho A2 V2, because rho is common. We are assuming incompressible flow density doesn't change, so we can just simply do A1 V1 equals A2 V2. You know the areas, right? So area is pi r1 square, and here the diameter is given. No, sorry, directly the area is given. Okay, so directly the area is given to us. So A1 is 0.1 into V1, which we do not know, and A2 is 0.02 and V2 is 50. So what is V1? Okay, 10 meters per second. Okay, so you can now just plug in the values and find what is P1. Density we'll take of air. Okay. So P1 minus P atmosphere is equal to density being 1.23, okay, by 2 into V2 square is 50 square minus V1 square is 10 square, And remember, we have to find the gauge pressure. So anyways, P1 minus P ATM is P1 gauge. This is what we need to find. So what is the answer? No. Please check your calculation. Yes. .476, yeah, kilopascals. Okay, that's right. All right. Any questions? Yeah, tell me. One question from. Can you speak loudly? Yeah. Okay. I think yeah, one of you typed is the same question. Yeah. Okay, I don't exactly know, but this is what he said. The position is not changing, but time is. No, see, this is I think related to what we discussed, right? Okay, let me go back to that derivation here. Yeah, these instantaneous radius. So here the acceleration is not due to the change in position. See, there are two ways you can get acceleration. One is because of change in position, one is because of change in the angle, right? Acceleration is dv by dt, and velocity has two things. Velocity has the like the speed, which is the numerical value, and yeah, and the direction, right? So acceleration can be because of change in the speed or because of change in the direction, right? So I think that's what he. Yeah. Okay, any other questions? Yeah, by the way, I quickly checked. This identity is correct. I will see how it's derived and get back to you next. Yeah. Yes. Okay. I think we can refer Crazy. It's a nice book. It's mostly maths. Spell it correctly. It's this. Yeah, Crazy. Or what you can do is Google some lectures on, not lectures, just notes on Einstein notation. Okay, so you can just Google Einstein notation for vector identities and see some proofs on vector identities. Like I have personally found the Einstein notation very useful. And if that's not the simpler thing for you, then you can start by proving simpler things like what A cross B cross C, right? You start with expanding these. You write three vectors, get the full form, then take the identity, take the right hand side, write its full form, and you can see that both are in fact the same. Okay, identities we can only verify. Yeah. Anything else? Okay, try and have a look at this derivation where we prove, yeah, for this irrotational flows, we prove that you can in fact apply Bernoulli's equation even on points which are at different streamlines.